Here we will learn to distinguish between vectors and scalars. Vectors are objects that have both a magnitude, a single number, and a direction, whereas scalars have only a magnitude. Let's see some examples of each. The length of something is a scalar because it's just the magnitude. A force exerted by someone pulling something is a vector because we care about the strength of the force, the magnitude, and the direction in which the force is acting. Temperature? It's a scalar. If we display temperature on a weather map where the value of the temperature is different at each point in space, this is a scalar field. In comparison, this weather map of wind, where the value of the wind velocity at each point in space is represented by a vector, is a vector field.
We begin with multiplication of a vector by a scalar. When you multiply a vector, a, by a scalar, this multiplicative factor just rescales the magnitude or the length of the vector. Let us look at the vector 2 times a. This is in the same direction as the vector a, but is twice as long. This is vector b. A vector is defined by its magnitude and direction, so this vector b is the same anywhere in space, including at the origin. If I want minus 0.5 times b, this vector is in the opposite direction of b and is half the length. Now let's look at vector addition. Here's a vector a, here's b. How do we add them graphically? We slide the tail of b to the head of a, and their sum is the vector drawn from the tail of a to the head of b. I could have also added a to b by sliding the tail of a to the head of b. You can see that this makes a parallelogram, and the sum, vector c, is just the diagonal of this parallelogram. Subtraction can be thought of as just multiplication and addition. If I have c is equal to a minus b, I just need to add a to the vector minus b. Minus b is negative 1 times b, which is this vector here. Now I only have to add a to minus b. Let's do another example. Here my vectors a and b do not start at the origin, but since vectors are the same anywhere in space, I can go through the process here. I want a minus b, so I first multiply b by minus 1 to find minus b, and then I move the tail of minus b to the head of a and add the two like this. For most of the problems we will be facing in the next few weeks, we will only need to work in 2 dimensions. We use a 2D coordinate system so we can formally put vectors on a grid and more easily do these vector operations. Once we have our axes, the next thing we need are unit vectors. Unit vectors have a magnitude of 1 and are in a defined direction. For our normal xy coordinate system, we have I hat in the positive x direction and j hat in the positive y direction. In Cartesian coordinates, the unit vectors are the same no matter what point in space we're at. We can also define a unit vector in the direction of an arbitrary vector. The key here is to make sure it has a magnitude of 1. We now look at representing vectors by their magnitude and direction. In this example, we have a force here. We can represent this force by its magnitude, which is the length of the vector, and the angle from the x-axis going towards the y-axis. We can also separately represent the velocity as a vector with its own magnitude and direction. Notice that in this example, the velocity is in a different direction than the force. Vectors can be represented through their components. If we have a vector A, we can decompose it into its components in the x and y directions by finding the vectors, one along x and one along y, that add up to the vector A. This is the same thing as finding the projections of the vector A along the x and y axes. Here is the projection of the vector onto the x-axis, its x component, and here is the projection onto the y-axis, the y component. This particular vector can be written as A is equal to minus 2i hat plus minus 2j hat. A generic vector in 2 dimensions can be written as A is equal to ax, the x component of A, times I hat, the unit vector along x, plus ay, the y component, times j hat, the unit vector along y. If the vector is in 3 dimensions, we will also have an az times k hat. What if we have the vector minus 3i hat plus 2j hat? First, we find the vector minus 3 times the unit vector I hat, and add this to the vector 2 times j hat. We can draw this vector anywhere. It doesn't have to start at the origin.
Let's look at going between representations. We'll start in the ijk representation, going to the magnitude and angle representation. So if we have our vector, the arbitrary vector could be written as ax I hat plus ay j hat. In this particular case, we're given a vector minus 2 I hat plus 3 j hat. And we'd like to go to the magnitude and angle representation. So first of all, let's draw it out on our grid like this. And let's find the magnitude. So the magnitude we can find through the Pythagorean theorem. It's just the square root of the x component squared plus the y component squared. And now we can find the angle. The angle, the tangent of the angle, is just equal to the y component divided by the x component, like this. And so in this way we can solve for the angle. Now let's practice going back the other way. If we're given a vector whose magnitude is 2 and whose angle from the x-axis is 30 degrees, like this one here, then the x component is just the magnitude times the cosine of the angle, so 2 times the cosine of 30, and the y component is just the magnitude times the sine of the angle, so 2 times the sine of 30.